computer. Okay. Okay, so today is September 16th, 2024, and we are continue covering the material on 1D motion. Okay, review the examples in the book. That would be the first thing that. But let's see. Before review the examples in the book, right? Review the derivations in class. You know, to prepare a list of equations. Okay, a list of important equations. Important equations. You know, set aside here and try to memorize them. And try to memorize them. Don't expect to memorize them right away, right? Don't expect to memorize them right away. Eventually, you end up memorizing those equations only after doing several examples. Okay. Let's see here. Yeah. Review the derivations in class. Prepare a list of important equations, try to memorize, and then review the examples in the book. Now, when you go look at the examples, not just examples in the book, but problems to solve, okay? However, be aware of problems that are poorly formulated, okay? That was I used to discuss those things with my professors there at the university. You know, there are many problems of that, even the ones in the book that are poorly formulated. You know, so the problem is not difficult to solve. This problem is just difficult to understand the formulation because it was poorly formulated. It was just like the case of the problem that was solving is Molly, right, Molly? That problem, that example in the book that we are solving there. Oh boy, that example was so poorly formulated, you know. It's that it was difficult to solve the problem, not because the problem was difficult, but because the problem was not formulated properly. Okay, it's amazing that that we have so many books that do things like that. Okay, in the case, it's the case of example 6, right? Example 6 in chapter 2, right? Example 6 in chapter 2 in the book. Chapter 2 in the book. Okay. So I take extreme care in formulating my problems during the exam so you don't get stuck in interpreting it properly. Okay. Example 6 in chapter 2 in the book, you know, it's unfortunate that they have formulated the problem in that way. But anyway, that's something that we have to live with. Okay. And so review the samples in the book. However, be aware of problems that are poorly formulated. And then, you know, try to solve as many problems as possible. Okay? Try to solve as many problems as possible. That I suggest you for preparation for the exams. Okay? Okay, and I'm gonna write it down here. Some, you know, but some problems are very simple to solve, but they are so poorly formulated that it becomes almost that is it becomes very difficult to interpret it and figure out to interpret it and to interpret it and find out what is being asked. So be aware of that. Okay. Try to solve as many problems as possible. Those are the 4 items that I want you to concentrate, okay? This problem, this example here too in the book, they formulated in such a poor way that, after going through that, this example is just what he was asking for. In this example, all he was asking is how long, I'm gonna, how long. Let me make sure this example 6 in the book, okay? So here you go. Molly, is that example 6 in chapter 2, Molly? Do you remember what was the problem we were solving there last time? I presume it was.
I think it was 2.6. I think
Was
you're
that?
right. I think you're correct.
Yeah, I'm correct, right? Yeah. So this problem could have been better formulated just by stating how long it takes for the Falcon, right, to displace a given distance. A given distance. That's all. That's all he was asking. Okay. So be aware of that. It's very important. Okay. It's very important that sometimes you're going to see problems that are very poorly formulated. And okay, now going back here to what we have, examples of 1D motion, right? And I still want to go to the book. Here we go. And Wiley Force Resources. Okay, we are here in chapter 2, equations of kinematics for constant acceleration, applications of the equations of kinematics, freely falling bodies, graphical analysis of velocity and acceleration. Let's see, let's take a look here at this one here, equation of some. Yeah, let's see. Example, displacement of a speedboat. Okay. Here you go, the peregrine falcon. That's the example here that I mentioned that's poorly formulated. Okay. This example here can be interpreted as a type of relative motion problem. Okay. It's so poorly formulated that even myself, when I look at that, I would interpret this problem as relative motion type of problem, which is further down the line, not now. Okay. So poorly formulated because okay, so in the applications of the equations of kinematics, okay, deceleration versus negative acceleration. Yeah, let's cover that. Physics of spacecraft hetero rockets. Okay. So okay, so let's I'm going to emphasize what the book here, what's the effect, okay? The effect of acceleration in the velocity and speed, okay? Velocity and speed. Here you go. Just remember that positive velocity means that the object is moving along the positive direction of the, let's say, x-axis. We're talking about 1D motion, right? That's what positive velocity means. Okay, negative velocity means that the object is moving along the negative direction of the x-axis. So let's illustrate that in the axis here. So let's see here. going to take advantage of this. Okay. Oh, no, not all I want. I want to do that. And now I'm going to put some dashes here. Here's the origin of my axis, okay? I'm gonna put this 0. And the other ones. One, two, three, 4. 5, right? Equal. That's my x-axis. Let's move to the center. Like that. And then I'm gonna get my x-axis here. X, where is my x? Here you go, this one here. And I'm going to label, not in centimeters, but I'm gonna label it in meters. Always keep that in mind. And we have this object moving from the right to the left. Okay, if it's here, is t equal to 0. T equal to 0. That's t naught, right? So let's say a little bit later on, the object, let's say it's right here at 1 second, right? Let's say here is 2 seconds. I want to make this guy a little bit smaller. Yeah. So you can see all the dashes there in the graph. I'll put the t equal to 1 second below, right? Do you recognize this type of motion right here? Here's gonna be 3 seconds. Here's gonna be 4 seconds. Here's gonna be 5 seconds and so on. Okay. In this case, the object is moving from the right to the left, from the left to the right. Okay. And because the object is moving from the left to the right, we denote this type of motion with a velocity vector. Velocity vector, I mean, with an arrow, okay? To the right. That's a good representation. Okay? And I even gonna label it V, this arrow with the letter V, which is what we call the velocity vector. The idea of vector we are going to study soon, okay? And there is more. Which type of motion do you think this is? Okay? Notice that the object is displacing the same distance for the same amount of time, right? For a delta t equal to 1 second, the object here between 0 and 1 displaces 1 meter. And further down, between 3 seconds and 4 seconds, the object is still displaced 1 meter. Okay, that is this is a different representation. This is another graphical representation of uniform motion. Uniform motion means constant velocity or constant velocity. Do you see that? Right? Specifically, the equation of motion for this graphical representation is going to be x, not capital X, but lowercase x, right? Equal to dt, okay? In this case, v is going to be 1 meter per second times t. Make sense? X naught is equal to 0, right? Where x naught is equal to 0. The initial position is equal to 0. Subscript. Okay, one more student is joining us. There's a name for this type of graph, for this type of graphical representation. Okay, I want you to find out what's the exact name for this type of graphical representation. Okay. Now, there is another type of graphical representation that's also important. Okay. And don't forget, because this guy here is a uniform motion, it means that the acceleration is equal to 0, right? Where, because it's uniform motion, the acceleration is automatically equal to 0. Then there's another. Okay, one more thing, right? At time t equal to 1 that I want to point out to you. The position of the object can also be represented by this other vector, okay? That's the vectorial representation of the position of the object. x1. If at time t equal to 1, at time t equal to 2 seconds, the vectorial representation of this other position is going to be this longer arrow. Did you notice that those arrows are only pointing in the same direction? The only thing that's changed is the length of the arrow. Okay? This is another vectorial representation of the position of the object at t equal to 3 seconds. Okay? And if this one here is x naught, if the initial position is x naught, then the next position, let's see, we can denote it by x1. Make sense? Right? Here you go. I'm going to put it here, x1. I'm not going to say the value, the numerical value of this position. Here you go. And I'm going to put this x1 here next to the first arrow, to the first position arrow. The other one is going to be x2, right? The other one is going to be x3. Okay. Now it's becoming very busy, this graph, right? This graph is becoming very busy. And so on. That would be x3, x4, x5, and so on, okay? Now let's go for another representation here, another representation of another type of motion, okay? Instead of having these dots evenly spaced, now those dots are going to, the spacing between those dots are going to increase as time goes by, okay? Here is t equal to 1. Here is going to be t equal to 2. The vector velocity, I'm going to erase this vector velocity for now. Okay, and this vector velocity here, let's say the initial velocity is equal to 0. Okay. Because the initial velocity at time t equal to 0 is 0, then we do not represent any velocity vector here. We just, the way we represent this velocity vector is going to be by a dot. Okay? A dot means an arrow that has 0 lengths. Okay, and I'm going to put it right here. Let's put t0, yeah, like that. And now this other one is going to be my v1, right? Raise it a little bit. The other one is going to be v2. And I'm even going to change the color, okay, to distinguish different quantities from one another. This one should be red. Red, okay. This one, instead of black, I'm gonna make it red. I'm putting them the same color to associate it with my velocity v1. And a little bit later, let's see, this guy is going to be, that would be t1. Okay, good. I'll keep a t with the black color. That's gonna be t2, but then at t2, notice that this spacing between each position is increasing, right? The delta x is increasing. Oh, this one a little bit more to the right. Because the spacing is increasing, it means that the velocity is increasing, okay? And if the velocity is increasing, my velocity vector becomes longer and longer, okay? Next one, let's see. Next one, remember it's increasing, right? The spacing here is increasing. So at time t equal to 3 seconds, it's gonna be a little bit longer. And that t4 is gonna be a little bit to the right. 3 seconds is going to be this one here. This one moved a little bit more to the right. And here we are going to have V3. Okay. V3. And this arrow should become longer. Do you see what's happening here? It means that the velocity is increasing. That's what this longer arrow means. The object is still moving to the right, but it's moving to the right at a higher velocity. Those are very good representations of the type of motion that we are studying. Okay, so here we go, that we have been studying. And I want the spacing to increase a little bit more, right? So here we go. So that's going to be t equal to 4 seconds. And the v4 velocity vector the only thing different between this graph and the previous one is the spacing between the dots, right? That's the only. But there is one more, and I want to do this exposition here with another color as well. Here you go, I like this color. Okay. And to distinguish that those are all different quantities. Okay, that's x1. The next one here is x2. The other one is x3, right? The other one is x4 and so on. And in this specific case, the equation of motion is going to be different. The equation of motion is going to be half at squared plus v naught t plus x naught. Okay, where x naught is 0 and v naught is also 0, because I stated here that a is not 0, a is different of 0, let's say. And I'm going to say that where x naught is equal to 0, comma, v naught is equal to 0, and a is greater than 0. I can erase those now. Okay. But there is one more thing. There is one more thing that I want to tell you. Compare this graph with this other one, right? And I'm going to, here you go. I'm going to do exactly what I did in the other slide with this one here. I'm going to change the colors of the quantities. It's not behaving the way I wanted. Let's raise it here. Need to give a little bit more of space here. Okay. Now we got it. Like that. And I came up with different colors for the x and their corresponding vector. Like that. Okay. Now there is one small difference between this graph and the other one. In this case, because the length of the vector velocity is increasing, we can also denote the vector acceleration. Okay? Because the vector velocity is increasing, we can also state Let's see, we need more space here. I'm going to reorganize that. Here you go. We can denote this other vector that we call the vector acceleration. Okay, and I'm going to copy all those V's here, and I'm going to paste it, but I'm going to paste it with a different color. You know, A naught, that's going to be A1, that's going to be A2, okay, A3, A4, and I'm going to place them, show them in a different color. Let's make it green, okay? This is green, this is green, this is green, and this is green. Are you getting the idea? And then I'm going to come up with the vectors too. But now, because the vectors are acceleration vectors, and because this type of motion is uniformly accelerated motion, the length of the acceleration vector is going to be the same throughout. Okay? And there is more. Because the acceleration vector is pointing in the same direction as the velocity vector, it means that the velocity vector or the speed, the length of the velocity vector or the speed is increasing. We see that? Okay? Okay. That's one more thing. I'm going to give you another example. What if the velocity here, initial velocity, is greater than 0? Okay? Another example. And now, here you go. Now, suppose that we have something completely different, okay? Suppose that we have this initial velocity here. It's not 0, but a larger velocity. I'm going to increase this arrow, okay? And instead of having this distance increased, the distance is going to decrease, okay? It is as though we have a mirror image of that. I'm going to put it like that. Just get a mirror image. Go. Those two. Okay. Going back. And now these two here. Notice that the distance now, the delta x, right? When I mean distance, I mean the displacement is decreasing. Okay. And I'm going to use exactly the same vector lengths that I was using before. Here you go. Okay. And V1 ends up being V2. This is another example. See the lengths? V2, I'm going to put it right here. Yeah, this one has to be in the middle better. So I have enough space. Okay. So I have enough space here. Yeah. And now V2. Okay. V3 would be this one here. Delta x here is decreasing. See that here we have a lot more than 2. Right here we have approximately 2. And 1, 2, 3. those two here now. This one is going to be t equal to 0. This t equal to 1 is going to be this one here. T equal to 2 is going, let's see, this one here. Okay, 1, 2, 3, 4. 1, 2, 3, 4, 5. 2, 1, 2, 3, 4. 2, 3. And now we need one more pair. I'm just taking the mirror image. Okay. Like that. That's next one. 1, 2, 3, 4. Right? 1, 2, 3, 4. Gonna be like that. Four. And finally, the last position here, we have this final velocity. I'm taking, like I said, I'm taking just the mirror image where the 0 vector here is represented by this dot that you see. Okay. So, and now what's happening here? Well, t equal to 0, 1, 2, let's see, this one is going to be 3, 1, 2, 0, 1, 2, 3, 4, right? 1, 2, 3, 4. Okay, we don't need this t equal to 5. We don't need this t equal to 5. Okay. And here you go. We have the position x1, position x2, position x3, and so on. Right? That's why it's so nice doing those things in computer, because you don't have to repeat the same drawings. All you copy and paste elsewhere. But then there is something wrong here with this representation. Okay? What is wrong with this representation? Which I'm going to correct, by the way. I didn't finish drawing this thing yet. Okay, one of the things that's not correct is the t square, right? Here's gonna be t square as well. What is incorrect is the acceleration vector. Notice that the velocity is longer here and shorter here, right? So how do you represent the acceleration vector properly? We represent the acceleration vector in the other direction of the velocity. Because the velocity is decreasing, we represent the acceleration in a direction contrary to that of the velocity. Okay? And because the acceleration is uniform, let me erase all those stuff here. 1, 2, 3, 4. Oh, not this one here. Okay, 1. And then I will get the acceleration letters in the proper place. Just bear with me, okay? 4. And we still have, okay, one more student here coming. Here is going, let's see, A1. This one is supposed to be A1. This one, let's see. Okay, this one here is supposed to be V1. Okay, so it's 4 here. We erase this one. V3, V2, and V1. Okay. And here we are going to have A0, A1, A2, A3, and A4. Okay, do you see what's happening here? When the acceleration, this type of acceleration, okay, is in reality negative. Whenever the acceleration is negative and the velocity is positive, okay, it means that the speed of the object is decreasing, okay? Okay, so that's what I want to get, and let's go 9:42. We still have some time. Going back here to the notes. Okay, positive velocity means that the object is moving towards, along the positive direction of the x-axis. Negative velocity means that the object is moving along the negative direction of the x-axis. Okay, now positive acceleration means that the acceleration points along the positive direction of the x-axis. Okay? Negative acceleration is the other way around, right? Negative acceleration means points along the negative direction of the x-axis. Okay? Then an object with positive velocity and positive acceleration, comma, means that its speed is increasing, okay? Remember, I put the word here, speed. When an object, here you go. When an object has positive velocity and positive acceleration, comma, its speed is increasing, okay? That's what you saw right in here. Now here's the other way around. When an object has positive velocity and negative acceleration, its speed is decreasing. Okay? And we can go the other way as well. When an object, I didn't illustrate those, okay, has negative velocity and negative acceleration, both the velocity and acceleration points in the same direction, its speed is increasing as well. Okay? And let's see. Negative velocity and positive acceleration, its speed is decreasing. I didn't illustrate these other two. I illustrated on those two right here. Okay? That's what you have to know about the signs of the velocity and the acceleration. And that's what we have right here, you know, in this chapter. Okay, see here, velocity to the right, acceleration to the left. In this case, the speed is decreasing. Velocity to the left, acceleration to the right, the speed is also decreasing. Okay? And so on. And now, let's see, we have 9:46 here. Let's take attendance, and then let's take a quick break, and then we are going to get into this very important example of uniformly accelerated motion, okay? Any questions about that? Let's see if there is any messages. No? Okay, so let's go get it. 16, Audrey Aguilar, are you there, Audrey? I can't hear you, Audrey. I can see that you're listed here, so I'm going to put a star. Next, Matthew Aguirre.
Hi, good morning, Professor.
Good morning, thank you. And Darius Blending. Let's see, Darius. I don't see Darius here. Yeah, I don't see Darius here. Next is Brianna Carrillo. Brianna, I see Brianna here. Are you there, Brianna? Looks like Brianna is away from. Oh, yeah, thank you, Brianna. Next is Jazzy Castellano. I don't see Jazzy here. Next is Gabriel Contreras.
Here.
Thank you. Liliana Cortez.
Here.
Thank you. Juan Escalera. I don't see Juan here. Next is Molly. Molly is here, right?
Yes, here.
Okay, thank you, Molly. Henry Kim.
Here.
Thank you, Henry. Ruth Mandujano.
Here.
Thank you. Noemi Martinez. Noemi, let's see. I don't see Noemi. Danae Miller.
Here.
Ramon Olivares.
Here, Professor.
Thank you. Taylor Forn.
I'm here.
Okay. Alexis Quijada. I don't see Alexis here. Okay. Jeremiah Reyes. Audrey Aguilar. Okay, Audrey. Stephanie Ramos.
I'm here, Professor.
Okay, thank you, Stephanie. Audrey Aguilar. Jeremiah. Let's see. Reyes. Yeah. I skipped Sean Rosario.
Here.
Thank you. Ali Standard.
I'm here, Professor.
Okay, thank you, Ali. Jason Strait.
I'm here.
Thank you. Elena Trujillo. Are you there, Elena? Okay, I'm gonna put a star here. Juan Escalera. Okay, Juan Escalera is here, right? Hi, Juan. I'm gonna put you a star here for now. Elena Trujillo. Let's see. Another chance here for Elena. Okay, leave the star for now. Jason Valadares.
Here.
Thank you, Jason. Stephen Padhapali. I don't see Stephen listed here. Next is Larell Williams. Hello, Larell. Elena, okay, thank you, Elena. I'm gonna put a star here in Larell. And Nuhamin Wandimu. I don't see Nuhamin here. Next is Alia Zavala. Hello, Alia. Okay, I'm gonna put a star here. Let's see how many students we have. So it's 19, 21, 21. Yeah, the numbers match. And let's have our break now. And break from 9:51 a.m. to Let's see, 10:06, 10:06 a.m. Okay. So I see you. Okay, Elena is here, right? Elena Trujillo. Yeah, good. So it's already here. So I see you in 15 minutes. Okay. Thank you. I'm back here. Okay, what you saw right in here, what you see right in here is what we call a motion diagram. Okay, and that's another representation of the motion of an object. So we have several ways. So we have several ways of representing the motion of an object. Okay, the first one is by equations, right? Using equations. Using the equations of motion. Using the equations of motion. Another way, two, by graphing x versus t, v versus t, and a versus t. And the other one, three, we have three, not several ways, let's put three ways, right? By using a motion diagram. Okay? So choose whatever you think is, you gotta know all of them, okay? You gotta be proficient in all of them. But there are those three here that we are covering. Going back to the book. Yeah. What you're going to do now, we're going to talk about free falling bodies. 2.6, okay. Graphical analysis of velocity and acceleration. We already covered that. Okay, and let's update, right, to what we covered so far. We did that before. Yeah, right in here. Material covered so far. Okay. Very soon we're going to start talking about that. We don't cover that yet. Displacement we cover, speed, velocity, acceleration equations of kinematics. Okay, and we did cover that. Graphical analysis of velocity and acceleration. And we did cover this one here as well. And now we're going to talk about this one right here, freely falling objects. Okay, we couldn't cover last time, right? Couldn't cover last time. Let's leave this way. One important application of the equations of motion, specifically the equations for uniformly accelerated motion, is the case of free-falling bodies. Okay? And that was a problem that was studied by Galileo. It was also studied by Leonardo da Vinci. They were trying to make sense of this important type of motion. Free fall. Definition of free fall motion. Definition of free fall motion. Okay? An object falling can be either falling or rising, okay? Falling or rising. So free fall does not necessarily mean that the object is just moving downwards. It also means that it can be moving upwards, okay? An object moving upward, let's see. An object moving downwards or upwards. Either way is considered free fall motion. An object moving downwards or upwards with an acceleration of g equal to 9.8 meters per second square. We usually approximate that to 10 meters per second square. Okay. So keep that in mind. Free fall means either upward motion or downward motion, not just downward motion. Here you go. I want this one. More students coming in. Henry is trying to get in. Good. Okay. In this case, the acceleration points downwards. Okay, point downwards. With the vector acceleration, here you go. With the vector acceleration pointing downwards. Pointing downwards, okay? If, here you go. If the object is moving upwards, comma, now you should already know, right? Its speed is decreasing, right? Similarly, if the object is moving downwards, its speed should be increasing, just like we covered before. So let's come up with our drawings here. Here you go. I have the case here of a freely falling object. And the first thing that I'm going to do, I'm going to write down the equations of motion. Remember, it's uniformly accelerated motion, right? So let's get our uniformly accelerated motion. So far, we're dealing only with polynomial equations, right? So it shouldn't be difficult to memorize that. So all the motions that we have covered so far are just described in as a polynomial. Here you go. No, not this one. No, not this one. Let's see. I should have them. Oh, this one right in here. Okay. More strictly speaking, the right way of writing down this equation is to write down with the acceleration first, because we start with acceleration, okay? In this case, the acceleration, and the second one should be the velocity, and the last one should be the speed. So should be the position. We don't need those two. Well, let's keep them. Let's keep them for now. This one. And now, how to choose? How to choose? I just told you that the acceleration is downwards. I didn't tell you anything about the sign of the acceleration, right? Notice that I only told you that the acceleration is downwards. I did not say anything whether the acceleration is positive or negative, okay? Notice that. Watch out. Watch out for that, right? In order to determine whether the acceleration or velocity, acceleration, velocity, acceleration, comma, velocity or position is negative or positive, we must first define our we define the direction of our axis. Okay, there is only one axis, and I'm gonna get there right now. So here you go. Going back here, I'm gonna take advantage of this drawing here, and the first thing that you should worry about. Suppose that we have. Okay, here you go. The first thing you should worry about is your x-axis, right? And that's what I have right in here. In this case of my x-axis, this x-axis must have an origin. Let's place an origin here in this x-axis. And let's label this x-axis with the number 0. Okay? Gotta put my origin a little bit more to the left. Let's see if it's a good, a little bit more. Even better, I'm gonna copy this guy here. Place it right here. Yeah, now the origin is in the right place. Just a little bit more, yeah, okay. Okay, so that's what I like to do with my student. Now I go, step by step here. So here you go. This axis must also have a y-axis. Oh, not this one. This one here. Okay. A y-axis. Right here, yeah. Make everything consistent. 1, 2, 3, 1, 2, 3. Okay, so here you go. Let's play the movie, right? That's what I call playing the movie. X-axis, origin of the x-axis, y-axis, right? The origin of the y-axis coincides with the origin of the x-axis. In the next drawing, I'm going to put a building to illustrate an object in free fall, okay? Here you go. Here's the building. And let's say we have our object that is initially at this position and is at rest at the top of the building, nearby the top of the building. Instant t equal to 0, initial speed is equal to 0. So I'm just releasing the object from this height, okay? You need the initial position of the object as well. And let's say we do not know this initial position. That's why I put this question mark in there. And we are going to observe this object moving downwards until it reaches a final position that's going to be impacting there in the ground. And this final position is going to be equal to 0. Okay? That's one way of doing that. And notice that I put my y-axis upwards. Here you go. Y initial is what we want to know. We want to find out what's the initial position of the object. And that's the type of experiment that you can do at home, right? You get an object, go to the top of a building. You want to know the height of this building, release it from rest, and watch the object until it impacts the ground. You time how long it takes for the object to move from here until it impacts the ground, and by using the equations of accelerated motion, you would be able to find out the height of the building, okay? That's what we are doing here. So given the initial velocity equal to 0, initial instant of time t equal to 0, and final position equal to 0, find the height of this building. That's what we're doing here. So here you go. Given example, right? Treated that as an example. Given the initial position, given the initial velocity of an object, let's see, example. You want, here you go, to find out the height of a building, okay? You release an object from the top of this building and time how long it takes to reach the ground. You release, okay? Release means v equal to 0. And time how long it takes to reach the ground. What's the height of the building? No? What is the height of the building? Okay. Solution, right? Okay, so it's like that. From the top of a building is better. And time, how long it takes to reach the ground. What's the height of the building? Okay. Solution. So what you do, you go ahead and you do this drawing. And remember that I told you that the acceleration of gravity is downwards, okay? So along the flight of this object, the acceleration is going to be downwards, g. That's the representation of g, lowercase g, okay? Which you already know is around 10 meters per second square. So the problem is the following. Given, now very important, because the axis is upwards, okay? The acceleration is going to be equal to minus g, which is going to be equal to approximately, right, meters per second square, with a negative sign. Okay, and here you go. That's a negative sign. G is always said to be positive, okay? Most books where G is always positive. Most books adopt this convention. And now we have our equations of motion. Okay, let's get our equations of motion. A is gonna be equal to minus G. It's minus G because I chose an upward axis here, okay? Minus G, which is minus 10 meters per second square. Okay. They remember that I'm releasing my object from rest. Consequently, V naught is going to be 0. Okay. My initial height is unknown. Y naught is, question mark. Question mark. Not this one. Let's see, this one here. My final height is going to be 0, right? Because I have chosen to put the ground exactly here at this height equal to 0. Okay. And now we can come up with our equations of motion. Okay. V is going to be AT plus V naught. Substituting those, those values. I'm not going to use everything, okay? But I'm just putting it here. So we have everything in our hands. Plus 0, right? Because V naught is 0, I don't need to write down V naught. X will be replaced by the letter Y, okay? By the letter Y. Y naught is the unknown, the one that we do not know. V naught, we know that's 0, so it can be taken out of the equation, and G is minus, and acceleration is minus 10 meters per second square. I'm going to put here between parentheses. Okay, this guy is not supposed to be here. And for now, I don't need those other two equations, but I want to keep them around for now. Okay. We want, and by the way, we do know, and I'm going to use some numbers here. U time, let's see, and time how long it takes to reach the ground. Let's see, T is equal to 10 seconds. 10 seconds, okay? What's the height of the building? You perform this experiment, and it takes 10 seconds for this object to reach the ground, right? T is goes right in here. Okay. So the height of the building is right in here. That's the one that you want to know. So in principle, we won't need this equation at all. But they are going to need this equation here. And we also know that the final height of the object is going to be 0, right? So let's concentrate on this equation alone. Okay. Substitute final height by 0. Okay. That's the equation that we want to solve. Here is going to be, I gotta put 10 seconds here as well, right? 10 seconds. Notice that I'm putting the units. Zero. Here, going to solve that is going to, the negative goes outside, right? 10 meters per second square, we can get rid of this parenthesis. We are going to square this term here. 10 seconds square becomes 100 seconds square. Okay. And y naught is what we want to find. We can go the next step here, that is simplifying everything. 10 divided by 2 is 5. We still keep the negative sign, and then we have to multiply by 100. It becomes 500. Note C. Okay, here you go. I'm just here writing my numbers here. Meters per second square times second square. I can go the next step, that's canceling the second square. We get just the meter. And now we can solve this equation, finally solve this equation. Okay, that's going to be 500 meters. Why not? Okay. 10 meters per second square, V not equal to 0. Okay, and minus 10, 10 seconds to the square, blah, blah, blah. Right, so I'm getting y naught equal to 500 meters. Did I make any mistake here? 110, 5. Here's 5, yeah. Yeah, doesn't look like I made any mistake here. Okay. A. A. So, A. What's the height of the building? B. What is another problem here? What is the velocity of the object just before it impacts the ground? Okay, so here goes. And now we can use this equation here. Okay, remember, I'm asking the velocity, I'm not asking the speed, right? B. To find the velocity, all you have to do is to use this equation here. Right? Substitute for t equal to 10 seconds. And we get minus 100 meters. This second cancel out with this other second here, right? And we get here minus 100 meters per second. And then we can go the next step. Instead of the velocity, what is the speed of the object just before it impacts the ground? Okay? So the speed is going to be what? The magnitude of the velocity. C. Let's write it down here. Speed, I'm going to use as S, is equal to, let's see, is that the one? No. Yeah, blah, 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 blah. Okay, I got this one here. This one, okay. Magnitude of the velocity. It's going to be 100 meters per second. And here is going to be SC. Okay, so that's a a simple example of this type of problem. But you can repeat it in a different way. Okay? You can repeat this problem in a different way. Repeat this problem for the case in which the axis, the y-axis is downwards. And the origin is right at the top of the building. Okay? Repeat this problem. You are supposed to get exactly the same result. Let's see. Yeah. You're supposed to get exactly the same result. Okay? And that would be the final position. That would be the initial position. Yeah. And that's the x-axis right in here. And then you want to go ahead and do that at home. Repeat this problem for the case in which the y-axis is downwards, and its origin coincides with the top of the building. Okay. I want you to do that on your own, to practice that at home. Okay. And and that here go. We have another example here. Okay. See, he's doing with the displacement. Here is the displacement. Okay, downwards. Okay, and then you can have other types of problems as well, a free fall problem. Repeat this problem on your own, right? On your own at home for the case in which the y-axis is downwards. And we can go ahead, we can come up with another problem that I'm gonna solve. Let's see if I have the illustration. Okay, so it's gonna be like that. This is gonna be 0 seconds. Here you go. So in this other problem, you know, I start with the initial velocity. This object, you know, is initially at height 0, right? And I propel this object upwards with the initial velocity. Here you go. Initial velocity that's known. Okay. I'm gonna put an exclamation point here, so it's clear that we do know the value of V0. Ooh. Oops. Yeah. V0 right in here. Okay, V0. Find the maximum height. I'm gonna put it max. Instead of y0, it's gonna be y max. Okay. This one is not YF. This one is actually Y0. Y0 is, okay. That's the problem that we're gonna solve. Repeat this problem on your own. And here goes. Next example. Okay. We propel an object upwards with a non-initial velocity. Okay, find the maximum height reached by this object. Okay? I'm gonna put that here as solution. So we do know the initial velocity, we do know the acceleration, and I want to know the maximum velocity, the maximum height. Okay? Think about that, how you're going to do. We do know that the maximum, when the object reaches the maximum height, right here, yeah. Oops. Yeah, that's good. Okay. Okay, so here you go. We do know that when the object reaches its maximum height, okay, and I'm gonna call it the maximum height correspond to the final position. Okay, final height. We do know that its final velocity is going to be what? It's going to be 0. Okay, this is not something that's stated in the problem, but that's natural to think about that, right? Maximum height, the object is not going upwards or even downwards. It's instantaneously at rest. Okay, so that's an important piece of information. The maximum height, the object is instantaneously at rest. In other words, Vf is equal to 0. Okay. Vf is equal to 0. So we can start using this equation here to find how long the object is going to stay airborne. Right? Here you go. Like that. I'm not going to do in numerical fashion. I'm just gonna do everything in symbolic terms, okay? So here you go. V equal to AT, and A is going to be minus GT because the axis is pointing upwards. Consequently, the acceleration is going to be minus G, okay? I'm gonna write it down here. EA equal to minus G, which is equal to minus 9.8 meters per second square, which is approximately minus 10 meters per second square. Like that. Okay. At the final height, this final velocity is going to be 0. Okay, and we can determine how long the object remains airborne until it reaches the final height, right? Equal. And then the next is going to be T equal to V naught divided by G. Okay? And now that I know how long the object remains airborne, we can find out what is going to be the maximum height that it reaches at this instant of time. What's going to be the final position of the object reaches at this instant of time. Okay, so all you have to do now is to replace, I'm going to boldface this one because that's the one we want to find out. Okay, here you go. Why not in this case is going to be 0, so I can erase it. V naught is not 0, is a positive V naught. T we can substitute right here. A is going to be minus G, right? MIT. Okay, V naught. Okay, I replaced everything. And let's continue solving the problem. It is V naught squared over G squared. I'm distributing the squares. V naught with V naught becomes V naught squared. I get rid of this one. G here cancels with this other G. Let's see if I'm missing any questions from you. No questions, okay. And this G here. And look what we get. We get half of V naught over G plus 1 V naught over G, right? So when we perform this calculation, we get plus half of V naught squared over G. That's going to be the maximum height. Okay, the maximum height that the object reaches. Let's do dimensional analysis to ensure that this result is correct, Let us test our final result to see if it's dimension, right? Units. It's dimension or units is correct, right? We're doing dimensional analysis here. Let us see if the unit of V naught square over G correspond to the unit of Y. 1048. We can go a little bit longer, right? So here you go. Unit of Y is equal to the unit of half V naught square over G. Half V naught square over G. Okay, that's what square bracket means, right? Unit of half V naught square over G is unit of half times the unit of V naught square over G. The unit of half is going to be 1. The number half has no unit whatsoever, it's a unitless unit. And the unit of V naught square over G is the unit of V naught square divided by the unit of G. Here you go. Here you go. Like that. Okay. In the next step, we don't need this one anymore, right? But we're going to need the unit of V naught square. The unit of V naught square is meter square over second square. And the unit of G is meter per second squared. Okay? Let's see if you get what we are supposed to get. second square cancel out with second square, right? We're even going to do a step by step here. Like that. Oh, here you go. Meters square over second square divided by meter over second square, right? That's what this ratio means, okay? Like that. But when you divide one number by the other one, we end up multiplying the inverse of the other number. Multiplication, let me get the multiplication. Yeah, here you go. Multiplication sign. It should be second square over meter. Second square over meter. And now do you see the usefulness of, second square cancel out with second square, right? I'm gonna put number one here, number one here. And this meter here cancel out with this other meter. And look what we get. We get exactly the expected unit for y, right? We already know that unit of y is meter. And then what we did, we found out the unit of v square over g, which is also meter. So that's two important examples of uniformly accelerated motion. And why are you solving for y naught and not y final, right? So let's see. Why not? Which problem are you referring to, Molly? 1049. This one I did. In this one, I solved for y. I didn't solve for y naught, okay? Okay, so here you go. Okay, so this is y naught here, right? This is y naught. And I want to solve for y final. And that's what I did, okay? Okay, this here you go. Y naught is given. And y naught is equal to 0. Let's see, where is my y naught here? Yeah, right in here. Okay, so I did solve for y final. I didn't solve for y naught, okay? I did solve for y final. Y naught is given, is known, and I should even put it somewhere around here. Y naught equal to 0 is better. Y naught is equal to 0. Y final is the one that we want to know. Okay? $10.54. Okay, so let's see if you have anything else here interesting. Yeah, those are different problems, okay? It's still a free fall problem here. You propel this object, the cannonball, at the edge of this cliff, right, upwards, and it reaches the maximum height, and then go impact here on the floor. Here, you propel it downwards with 30 meters per second as well, right? And let's see what he's asking here. Conceptual shows a pellet that has been fired straight up from the edge of the cliff. The initial speed of pellet 30 meters. It goes up and then falls back down, eventually hitting the ground beneath of the cliff. Okay. Has been fired in the absence of air. Would the pellet interactive strike the ground with a smaller speed than B or C? Okay. That's what he's asking. One more student here. And by the way, it's very important. Those equations are applicable. By the way, these equations are applicable only in the absence of air friction, okay? And that was something that Galilei was struggling at that time to explain his peers, okay? If you go back here to the book, you know, we have a very important illustration of the feather, okay? Falling in a tube. In this case here, the tube is filled with air. Okay, feather in a rock, right? Let's see, paper in a rock, paper in a rock. Okay, if you release both of them at the same time here at the top, because this tube has air, the rock is going to reach the ground first, the bottom first. Okay, but if you evacuate the tube, if you eliminate air friction, then both of them are going to reach the ground at the same time. The ground, the bottom here of the tube at the same time, okay? And these equations are applicable only in the absence of air friction, okay? There is a very nice experiment. I'm gonna put experiment between quotes. Experiment performed by an astronaut on the moon's surface. With a hammer and a feather. Okay? There is no air on the moon's surface. So when he releases both objects simultaneously, they reach the ground at the same time. Okay? Try to find this video. Maybe we have it here. What time is that? 2 more minutes to go before our break. So astronaut performing free fall experiment. Let's see, on the moon surface. On the moon surface. Let's see if we can find it. We cannot find it. You may walk videos and relative free. Let's see. Hammer and feather experiment. Yeah, that's the one. Let's see if they have it, the recording here.
Build strength over 35.
Let's skip it.
Or this, or doing it.
Skip it.
During the Apollo 15 lunar mission in 1971, an astronaut named
1971.
Scott dropped a hammer and a feather simultaneously from rest to demonstrate that the two objects would fall at the same rate in the absence of atmosphere.
Yeah, they don't have the
So
video,
as you can see, the experiment
unfortunately.
worked out. And in this problem, we're going to investigate the free fall kinematics that was going on.
Okay, yeah, they don't have the video. Maybe it's this one here. Hammer versus feather. Yeah, it must be this one. Let's see, this one here.
Cam, we copied both solar wind and Tennis drum in the ETD.
Yeah, here you go. Here you go, the astronaut on the moon surface. Here you go, the hammer here.
I want to watch this. A good picture there.
Beautiful picture, Dave.
That's terrible picture. For comparing for today's standard, this is a terrible picture, right? Remember that's 1971, right? And this transmission was being done from the moon surface, 300,000 kilometers away from the Earth.
Well, in my left hand, I have a feather.
A feather.
My right hand, a hammer.
A hammer.
I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Yo, yeah, see that? They reach the ground at the same time. No, notice that they fall slower because the gravity on the moon is lower than the gravity on the Earth, right? On the Earth is 10 meters per second square. On the Moon is 1/6 of that. There's 1 point whatever, 10 divided by 6, 1.67 meters per second square. Okay.
Now the
There you go.
correct in his findings.
Do you see how the astronaut seems to float? They're not floating. They're just being accelerated at lower rates. And that's how they end up walking on the moon, like a kangaroo. Okay. So 11:01, let's take our break now. Break. Any questions? 11:01 a.m. to 11:16. Let's close this one here. Yeah, so you don't. Any questions before you go to the break? So we are done with chapter two, okay? And then now I'm going to start chapter number 3. So I see you in 15 minutes. I'm back here and let me help you out with some more realistic motion diagrams, okay? Remember what I showed to you here? Those are called motion diagrams, okay? It's just like a movie. That's what it is all about. It's a movie, right? The particle is initially here, then it moves here, and so on. Okay. What I'm going to do, some time ago I made a motion diagram in Excel. It's possible to do those motion diagrams in Excel. I'm gonna put it right in here in our notes, and it is in the 2023 notes as well. Okay. Let's see here. Motion diagram. Motion diagrams. That's for uniform motion. Motion diagrams. Uniform motion. Okay, you can see that the spacing are exactly the same. Okay, you can do something like that in Excel, like I mentioned. And here you go. Description here of this motion diagram of a particle undergoing uniform motion for x not equal to 0 and v equal to 1 meter per second. The time separation between each consecutive dots is half second. Okay, and this one is the motion diagram for a particle. The next one is the motion diagram for a particle undergoing uniformly accelerated motion. Now what you see here is far more realistic than what I drew before, because I was doing just out of in a qualitative fashion, but here are actual calculations, okay? Particle undergoing uniformly accelerated motion, x not equal to 0, v not equal to 0, and acceleration 1 meter per second square. The time separation between each consecutive dot is, okay, is half a second. Okay, half second, 1 second, 1.5 seconds, 2 seconds, 2.5 seconds, 3 seconds, and so on. Okay, the distance increases. Okay, and now we are going back here. Material cover so far. Really falling bodies. So now we covered everything. Chapter 2. Okay, this one we covered for everything, including uniformly accelerated motion. We can erase this guy here. It's not applicable. Okay, prerequisite for the course, yeah. So chapter 2 is done, and we're going to start with this section now. Okay, so at this point, folks, you should have a qualitative idea of vectors already. Okay, at this point, you should already have a qualitative idea of vectors. Okay, I gave you an idea how vectors behave. They can be represented by an arrow. Okay, but more specifically, vectors is just a type of different number. Okay, when we are learning the first things in math, the first steps in math, right? First grade school, we learn about numbers, and we have this idea of numbers is very useful because it helps us with several real life situations, like keep track of your money, you know, exchanging money with someone else, and other things. Okay, so by the same token, that numbers is a abstract tool. That's what numbers is, an abstract tool that we invented to make life easier for us. Okay, we have invented through this other abstract tool, this other mathematical tool that we call vectors. It helps us to solve problems in a much more efficient fashion, again, in a much more simpler way. Okay, I like to tell my students that vectors are a type. Vectors is a type of number that has an additional piece of information. Okay, whereas numbers tell us only the magnitude of something. Okay, a vector has information on the magnitude and direction of something. That's the main difference between vectors and numbers. Okay, numbers carry with themselves only the information about the magnitude of something. Vectors is a more complete concept. Carry with them, okay? A more complete concept. A vector has information, carry information about the magnitude of something, right? And I'm just repeating, right? Its direction. That's the important difference between vectors and numbers. In physics, okay? In physics, we have numerical or scalar, okay, quantities, as well as vectorial quantities. Not everything is a vector. Not every physical quantity is a vector. Okay? Not every physical quantity is a vector. And now we should go back to that table about the core principles of physics. Let us go back to the table. Listing, right? Listing the core principles of physics. I want to simplify this table here. Yep. Okay, and that's what we have here. Let's see, one more. I want to fit this in this line. Okay, good. So here you go. Remember we had the basic quantities of physics and the primary definitions, right? We still didn't cover any laws of physics, so let's skip that for now. A little bit more of space here so you can. Okay. Well, not only we have this basic quantity here on the left side and the primary definitions, but I guess I mentioned that before. The basic quantities, they are always scalar quantities. Length, time, mass. You know, there are 4 more. Whereas the primary definitions, they are vectorial quantities. The position, right, is a vector quantity. And the force you're going to see soon too is also a vectorial quantity. Okay, but like I said, just like I mentioned, not every quantity in physics is a vector. We also have scalar quantities, right? And that difference between scalar definitional differences. The difference, there's a difference. There's a difference between a scalar / numerical quantity and scalars like numerical and vectorial quantities, okay? So let's start listing, right? Some examples, right, of scalar and vectorial quantities. I'm going to list all of them that we have covered so far: length, time, mass, distance, and speed. We didn't mention anything else, right? That is a scalar. Vector, position, force, displacement. Okay, which, by the way, in physics, we usually represent a vectorial quantity by a letter with an arrow at the top, okay? In the case of the position vector, we represent it by the letter R with the vector at the top, with an arrow at the top. In the case of the force, we represent a vectorial force with the letter F with an arrow at the top. For displacement, it's going to be delta R because it's a difference in position, right? For velocity is a vectorial quantity as well, we represent that by the letter V with an arrow at the top. That's the important notation here, arrow at the top. But you will also see in many books that this notation of a vector can also be represented by bold-faced. Okay, some books, instead of putting the arrow there at the top, they just bold-faced the quantity. Okay, in the case of the force, it's the same thing. They bold-face the letter F. Okay, they bold-face our delta R. That's another way without the arrow. That's another way of denoting vectors. Velocity, similarly, V, bold-faced V. What else? And then we have acceleration, right? Acceleration, which is also a vector, can be an A with an arrow at the top or an A that's bold-faced. Okay, I prefer to use this notation here with an arrow there at the top. I prefer to use, and most books prefer to use also the notation with the arrow there at the top. Okay? So, and here is let me get the other slide. Illustration, vectors. Yeah, here you go. Vectors. Okay, here's a representation of a vector. I'm calling that a vector A. This vector is represented by an arrow that's making an angle with the horizontal direction. Okay. This vector, now I have two vectors, vector A and vector B. They both have the same lengths and they have the same direction. They are angled at the same angle with respect to the horizontal. Because of that, because they have the same magnitude and the same direction, those vectors are said to be equal to each other. Okay? And I can even play the movie here for you, right? So we start here you go, a mathematical entity that has magnitude and direction, right? So in the next movie, I just represent the arrow. No? It can be represented by an arrow. Graphically, here you go. Graphically, it can be represented by an arrow. Mathematically, it is represented by a letter with a arrow at the top. Okay, so graphical representation of a vector, mathematical representation of a vector. Okay. In the next slide, here you go. In the next slide, I'm going to put a direction, horizontal direction. And I'm going to denote this direction with an angle. Okay? So playing the movie again, right? Here you go, arrow. I'm gonna break down into two slides, okay? Here you go. A vector is a mathematical entity that has magnitude and direction, okay? Graphically, here you go. It can be represented, a vector is represented by an arrow. Right? Let's see. Right in here. Here you go. An arrow. Here you go. Should be the right direction. The right graphically, a vector is represented by an arrow. Mathematically, to the direction. Let's see. An arrow. Yeah, we don't need this one here. Mathematically, this is represented by a letter with an arrow at the top. An arrow at the top. Okay. We don't need this horizontal here. Next, here you go. The direction of the vector must be represented with respect to the horizontal or vertical, right, direction. And here I have the horizontal or vertical direction, right? And here we have the horizontal direction and the angle with respect to this horizontal direction. Okay. Arrow, graphical representation, mathematical representation. The representation must be taken with respect to a horizontal or a vertical, depending, right? How do you define it? And you document the direction of the vector with respect to this horizontal direction, for instance. We don't need that anymore. Good. Next. Okay, if two vectors have the same length and direction, they're equal to each other. Okay. If two vectors have the same direction but different lengths, they are different. Okay. In this case, the magnitude of vector B is greater than the magnitude of vector A. Do you see the symbol for magnitude here? Okay. Those vertical bars. Okay. A is different of B, but and in this specific case, the magnitude of B is greater than the magnitude of A. Okay. Here's another set of different vectors. You can have a vector that's pointing in this direction, to the right, but then a vector of same length, same magnitude, but pointing the other direction. This is vector A. Here's the vector minus A. Okay, they have the same angles, right? Same magnitude, but different direction. Okay, vector C is different from A, and all those vectors are different from each other. either because they have different directions or different magnitudes. Okay? Here you go. We can make operation. We can operate with vectors. Let's go back to our notes here. Okay? We can operate with vectors. No, even better. By the same token that we can operate with numbers and scalars, comma, we can also operate with vectors. What are the type of operations? What are the types? And here are some operations we can make with vectors. Some of the operations we can make with vectors. Okay? 1. We can multiply a scalar with a vector. Okay? So just like here you go. A scalar here I'm going to represent by the letter C, okay? C times R. Right? C times R. Better. Okay. Where C is a scalar. Scalar. And here is an illustration. Here you go. If I have this vector A and I multiply a number C, and the scalar C, by A, where C is greater than 1, then the vector A becomes longer. It's no longer is vector A. I'm calling it now vector E. Okay? Now, if we have another scalar multiplying my vector, a scalar A that has a value between 0 and 1, then the vector is going to become shorter, right? One of the operations is vectors. Multiplication of a vector is a scalar, is a number. But those scalars can also be negative, right? We can divide. You can divide a vector by a scalar. If the C is less than 1, the resulting vector is going to be shorter, right? Similarly, if this other scalar is between 0 and 1, when we divide the vector by this scalar, the vector becomes longer, okay? So let's 1, 2, we can divide a scalar, divide a vector by a scalar. So let's say R divided by C, right? Where C is a scalar. Here you go. If C is greater than 1, then the resulting vector is longer than the original vector. Okay, like that. If C greater than 1. If C less than 1 and greater than 0, right? Then the resulting vector is shorter than the original vector. right? Let's do that. If C is equal to -1, let's put it this way, equal to if C is less than 0, then the resulting vector changes direction, right? Will point in the opposite direction, right? We can also divide a vector by scalar, right? What else can we do with vectors? 1146, okay. Division, multiplication by scalar, okay, we covered that. By a negative, here you go, when we multiply a vector by a negative number, the angle between the vector and the direction is changed by pi, 180 degrees, okay? Let's write that down here. We can divide a vector when then the resulting vector will point in the opposite direction and its angle will be phased out by 180 degrees, like that. Okay. Okay, so here you go. Another example of a multiplication of a vector with a negative number, okay? And here's the representation of 3D vector. What you have seen here, they are all representation of 2D vectors, but vectors can also be represented in the three-dimensional space. Here's a representation of the 3D vector to give you the illusion that this vector here is floating in space, right? X-axis, Y-axis, and Z-axis. Okay, what else can we do with vectors? Which other type of operation can we do with vectors? We can also sum vectors. Going back here, we can sum vectors. For instance, you know, the simple summation between vectors is going to be this one I'm going to show you. When I sum the A vector with the A vector, what do we get? We get twice the original vector. Okay, and let's unbolt this. Make sense? Okay. We can also sum A with another vector, with a different vector, B. Okay, but it's not going to be necessarily equal to 2A. Okay, it should be another vector that I'll call it C. Okay, here you go. And that there is this graphical method to obtain the resulting vector, okay, what we call the head to tail method. So what we do with the head to tail method, we get one vector and place at the tail of the other vector. This vector here is placed at the tail of the other vector, resulting in this longer vector that you see right here. Okay, let's write it down here in the notes. Okay, vectors, we can use graphical method. We can use a graphical method to determine the resulting vector. When we sum, right? Let's put it here. When we sum two vectors, we can use a graphical method to determine. We can use two graphical methods to determine the resulting vector. The first method that I told you is the tail to head method and the parallelogram method. You saw the tail, head to tail, not tail to head, let's see, head to tail method. Head to tail method. And the parallelogram method. Okay? Here you go. Head to tail method again. A and B. A plus B. Right? That's the resulting vector. Head to tail method again. You know? B plus A. Okay? You end up getting exactly the same vector. Because it points in the same direction and has the same magnitude. So, you know, here you go. Property of the summation of two vectors, right? Property of vector summation. They are commutative. Commutative, here you go. Commutative means what? A plus B is equal to B plus A. 1152. Okay, here you go. Commutative property of vectors under summation. B plus A plus B. Okay, here you go. In this specific case, because we have vectors in the same direction, their summation coincides, the magnitude, right? The magnitude of their summation coincides with the summation, sum of their magnitudes. But that's because it's a special type of two vector summation. It's not, this thing doesn't always occur, okay? Now, what happens when we sum two vectors that have different directions? When you sum two vectors that have different directions, we can use the head to tail method, but can also use the parallelogram method. Let's show you how you do it, how you can do it. Using the head to tail method, vector A and vector B. Here you go. Put the tail of B at the head of A. And then connect the tail of A to the head of B. Okay? That's a more complicated example of how to sum vectors. Okay, so here you go. But we can also use the parallelogram method. In the parallelogram method, we put the tails of both vectors coinciding with each other, and then we draw a parallelogram out of these two vectors, and then connect one edge here of the parallelogram to the other edge of the parallelogram, okay? You gotta practice that so you become very familiar with those properties. Okay, so here you go. I'm gonna copy and paste here. Properties of vectors and paste. And then you can also subtract vectors. Here you go. Here you go. Okay, vectors can carry, right? Vectors can be multiplied and divided by scalar. Is nothing but A plus BA. Vectors same direction, but distinct magnitudes are different of each other, blah, 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 okay? And then you can also subtract two vectors. Let's see. Let's take a look at how we subtract vectors here. Let me see if I have an example of subtraction between vectors. Okay. Subtraction between vectors. And then this thing is supposed to be elsewhere. Okay, let me. This one supposed to be right in here. Here you go. Subtraction between vectors. All you gotta, if you want to subtract A minus B from A, all you have to do is to sum A with the negative of B, okay? And that's displayed right in here. I'm gonna do even better, is A minus B is equal to A plus the vector minus B. Make sense? Okay. So here you go. If B is upwards, right? Then I go ahead and sum tail to head method. Okay, here you go. A and B. Let's see here. Parallelogram method. Okay, so. Okay, this one belongs elsewhere. Yeah, I can erase that. Let's see here. Yeah, let's skip that. But that's the important thing here that you have to know. Okay, the subtraction between two vectors is like summing one vector with the negative of the other. It's 11:58 right now, and let's stop here. Let me see if I want to make sure. Juan Salvador Escalera, are you there? Want to give Juan another opportunity here to make himself known that he's here. Are you there, Juan? Okay, thank you. And there is one more student. Let's see. Alia, are you there?
Yeah, I'm here.
Okay, thank you. Now we have 21 students. Okay, any questions? Okay, so let's stop now. I have a break. I have office hours right now. If you want to hang around and talk to me, okay. I'll be here. Otherwise, I see you on Wednesday. Okay. I'll see you the day after tomorrow.
Thank you, Professor.
Welcome.
Are the office hours here as well?
Yeah. Who is that?
That's Ramon. I was just wondering if I can be excused from Wednesday's class because I have a work thing that I have to do. Is there a way I can I know it's a lab day.
If you miss that lab, you're going to, you're not going to get credit for the lab, okay? That the activity that we do. But anyway, I dropped one of the lowest grades, okay? It's very important that you're.
Are we continuing the same charts that we were doing last week?
Yes, that's right.
I completed all three of the graphs for that one.
Well, there is more to do. It's not just the graphs. We have other stuff to do. Okay, so it's important that you reserve. It's important that you reserve the Wednesday to be present. Because the lab accounts for rather of a large chunk of your grades. If you can switch, Wednesday to Monday would be you'd be better off.
Okay, I'll talk to them. Thank you. Have a
Welcome.
good one.
You too. Thank you, Jeremiah. Bye-bye.
Academia aí mesmo.
Outros. Deixa eu ver o que eu vou fazer. Essa aqui é uma foto.